This video deals with angular velocity and linear velocity, and trying to give you some things to compare here. We're going to be talking about the Earth orbiting the Sun and talking about the spin of the Earth on its axis. So I looked up some data using the internet. So the Earth's orbit is not circular, it's elliptical. But if it was circular, we could say its radius would be this number, 1.496 times 10 11th meters. The Earth is not spherical, but if it was a sphere, its radius would be 6.378 times 10 to the 6 meters on average. So I've got a website here where these numbers came from. The time for one orbit of the Sun, it's not 365 days, so we've got 365.2422 days. This leads to leap years, and then there's another special rule for why some years divided by 4 are not leap years. Minor topic. The time for one rotation of the Earth with respect to the stars, not with respect to the Sun, with respect to the stars. So a sidereal rotation of the Earth, 23 hours, 56 minutes, and 4 seconds. And do a Google search for sidereal if you want more information on this, but it's measuring the rotation of the Earth with respect to a distant star. So here are our calculations. We want the angular velocity for the Earth orbiting the Sun. We want the angular velocity of the Earth due to its spin motion. And then we want to find the linear velocity, the meters per second, for the Earth in its orbit, and for a little something on the beach on the equator of the Earth due to the rotation of the Earth. So let's talk about the angular velocity of the Earth orbiting the Sun. The angular velocity is how much angle we've covered, and standard unit is radians of angle, in a certain amount of time. So we're going to come up with radians per second for our answer here. Well, in one orbit of the Sun, that's one full circle. That's 2 pi radians. That's the angular distance traveled. And what about the number of seconds for one orbit? Well, we were given 365.2422 days for the time for the Earth to go around the Sun once. There are 24 hours in one day, so there's a day unit. And then the solar day would be getting the Sun back directly south. How much time has elapsed? So that's 24 hours in a day. 3,600 seconds in an hour. So I get 3.1557 times 10 to the 7th seconds for a year. And just a curiosity here, if you don't want to look this up, roughly it's pi times 10 to the 7th seconds for a year, as if you don't need an exact number. Well, what's the angular velocity? How much angle we traveled divided by the time. 2 pi radians is the angle we've covered in one orbit, and we just worked out the amount of seconds, so I got 1.991 times 10 to the minus 7 seconds, or could round this off to 1.99 times 10 to the minus 7 radians per second. Well, what about the Earth and the spinning action of the Earth? The same angular velocity. How much angle did we travel? How much time is required? Our angle, again, is 2 pi radians, one spin of the Earth. For the time, converting hours to seconds, converting minutes to seconds, adding on the 4 seconds, I got 8.6164 times 10 to the 4 seconds. This is not the number of seconds in a solar day. This is a sidereal day, a spin with respect to the stars. So again, doing the division here, 2 pi radians for one circle, one spin. The time that we came up with, 7.292 times 10 to the minus 5 radians, if you want 4 digits. 7.29 times 10 to the minus 5 radians per second. But we have a linear velocity to calculate next. Linear velocity will use the angular velocity we just had. The linear velocity is the radius times the angular velocity. Well, so we have the Earth in its orbit, this distance from the Sun, and that's why I kept the 4 digits, because I knew I was going to need this angular velocity later. So to get a little more accurate. 1.991 is more accurate than 1.99. But multiplying those out and rounding here, this final answer, 2.98 times 10 to the fourth meters per second. You may not have a good sense of what meters per second speed is, so I'm converting it to miles per hour here. 67,000 miles per hour. That's considerable. 67,000 miles per hour. That's the linear velocity of the Earth in its orbit around the Sun. We're going to take advantage of that later in a bonus calculation at the end of the video. What about the linear velocity at the edge of the Earth, on the equator of the Earth, for this grain of sand? Well, again, V equals R times omega, radius times angular velocity. 6.378 times 10 to the 6 for average radius of the Earth. Then we have our omega here, our angular velocity we calculated earlier. And I'm rounding off here, 4.65 times 10 to the 2 meters per second. Again, to put this into something we're more used to, miles per hour, 1,040 miles per hour. So I'm going to go on to a little bonus calculation. Suppose the sun disappears, its effective gravity disappears. Well, the Earth's going to move off in a straight line from its orbit at this speed that we had. How long would it take us to get near the star Pollux? Pollux happens to be a bright star that's relatively near the path of the sun on the sky, called the ecliptic. So if we, in this problem, take away the sun at the time the Earth is basically, its velocity is pointed towards the star Pollux, let's calculate that time. So this is sort of interstellar travel. Pollux, 34 light years away. The closest star is about 4 light years, other than the sun, is about 4 light years away. So this is still relatively close. Suppose people want to travel to other stars. How feasible is that? Well, distance equals rate times time, constant rate. If we get rid of gravity, we can assume our Earth's velocity will be constant in direction and magnitude. If there's no gravity to worry about, not going to worry about other stars along the way deflecting our path. Physics problem, to simplify it to Pollux is the only star in the universe. Distance equals rate times time. If I divide by rate on both sides and call it now speed, time is distance divided by speed, or distance, converting light years into meters. You get 3.22 times 10 to the 17th meters to get to Pollux. And our speed we worked out previously. So our time is distance divided by speed. And I came up with 1.08 times 10 to the 13th seconds. That sounds like a big number. How many years is that? Well, let's divide by the number of seconds in a year. And we get 342,000 years. That's how much time it would take the Earth to move from where we are now. If the sun disappears, there's no gravity, and we maintain this speed for the whole time moving towards a star, 342,000 years. Distances between stars are tremendous, and our technology now for rockets does not involve warp drive of Star Trek fame. It's not feasible with our current propulsion technology. So 342,000 years for the Earth to fly off and get near this star Pollux. I've got lots of astronomy and physics YouTube videos. They're organized by topic at gpclements.com, my simple website. The annotation is there's a title, there's a description of how many minutes the video lasts, a description of the video, and then most useful, there's a direct link you can click on to get to the YouTube video. You don't have to go to YouTube and search for the videos. These are organized by topic here. I do have playlists at YouTube on my channel that help also, but this is, I think, a little better for helping people find the videos that are interested in. All the content I create here is free. You can't resell it, but you do not give me your name or email address, anything. No payment. And my website does not put cookies on your computer. So I hope you keep working physics problems. Again, at this website, Most of them are physics problems, over 300 videos for physics, maybe 150 for astronomy, getting up towards 400 for physics, and then some computer videos, some math refresher videos. So I hope you use them and hope they're useful to you. Ask your instructor if you have questions.